Welcome, everyone. Well, we're going to start integration now. So we've been looking at our scalar valued functions, and we've seen how to differentiate them using partial derivatives. Well, now we're going to look at kind of the counterpart to that, and that's partial integration. And we're going to see how this applies to the concept of double integrals. So we're going to jump ahead a little bit in the notes here, and we're going to come back to the discussion of what the double integral actually is, and it has to do with volume. But let's jump ahead a little bit in our notes and just get a little taste. Well, here's our definition of double integral, so we're going to unravel that. But let's get a little taste of how the integration process is going to work, and then we'll come back and talk about what we're actually doing. And this has to do with what we call iterated integrals. And the concept here is we're going to be doing partial integration. So that's really the idea behind how we're going to calculate these things called iterated integrals. So think of this as like the counterpart to our partial derivatives. Now we're going to be doing partial integration. All right, so what does the notation look like? Well, let's suppose that f is a function of two variables and we can integrate it. We'll see what that means in a little bit. And we're going to be looking at a rectangle where the x coordinates are between a and b and the y coordinates are between c and d. We can calculate this integral. So the integral of our function f of xy with limits of integration from c to d, and we're integrating with respect to y. So how we would calculate something like this is the information here we're getting from this differential dy. And you can see the limits of integration are for the y coordinate. And so what this means, how we're going to calculate this, is we're going to keep x fixed. So any x's that we see in our function, we're going to keep those, we're going to treat those as a constant. So think of x when we see it as a constant, and then we're just going to do the antiderivative of the y terms like usual. So that's kind of like what we did with partial derivatives. If we were doing the partial derivative with respect to y, we would treat x like a constant and then just differentiate the y terms like usual. Now we're seeing a little bit of the notation for this idea of partial integration. We might also do, say, the x integral. And we get that from the differential here, the dx. So that's telling us we're going to treat x like the variable and y like the constant. So in this case, y is held fixed. So we're treating y like a constant. And when we integrate, we're going to integrate the x terms like usual. And if it's a definite integral here, we can see that the limits of integration then are for what x is doing. So x is between a and b. All right, so let's see a little example of what this partial integration looks like. So we're going to jump ahead, and we're going to look at example 4. All right, so this is what's called an iterated integral. And the way we do this is we read the iterated integral from the inside out. So the first thing we're going to do is this integral on the inside. So that's what we're going to do first. So let's just write that down. So we're going to do the integral from 1 to 2 of x squared times y dy. So now this differential here is telling us we're going to integrate with respect to y, and we're going to hold x fixed. So that's what that dy is telling us. So x is going to be like a constant, and y is going to be like our variable term. So it's kind of like when we did partial derivatives, it's kind of what we did there. All right, so let's see how this is going to look. So we're looking at our function here, the x squared y. X is like a constant, so we're going to integrate that y term. And when we do it, we use our power rule for integration. So we add 1 to the exponent, take that new exponent, flip it, put it in front. And so we get our antiderivative here in terms of y. Again, we were treating x like a constant. And then we're going to evaluate this from y equals 1 to y equals 2. So kind of very similar to how we would do just a regular definite integral. We get the antiderivative, and then we're going to evaluate. And so when we evaluate, the top number is going to go in first. So we're going to plug y equals 2 in. And when we do that, we get 1/2 times x squared times 2 squared. So we're only plugging in for y. That's why it's helpful to kind of write y equals, just to help emphasize. Then we subtract, and then we plug in the lower number, the 1. So we get 1/2 x squared times 1 squared. And if we clean that up, we end up with 2x squared minus 1/2 x squared. And we want to try to simplify this down as much as possible. So if we go a little bit further, we end up with 3/2 x squared. So note, once we do this partial integration here with respect to y, all of the y terms should be gone then in our result. So just a little note here about our result. Only x terms and constants should be left. All the y's should be gone. All right, so that's we've done the inner integral here with respect to y. And now we're going to take this result and we're going to plug it in right up there. So our result here was the 3/2 x squared, and we're going to fill that in. So we're going to have the integral from 0 to 3, and then instead of this inside integral with respect to y, we're plugging in the 3/2 x squared. All right, so there is our new integral to do. And now this is just a regular definite integral that we saw back in Calc 1, or maybe 2. All right, so power rule. And when we do the antiderivative, we end up with 1/2 x times x cubed. And then we're going to evaluate from x equals 0 to x equals 3. And then when we do the evaluation, top number goes in first. So we end up with 27/2. And then we plug in the bottom number and subtract, and we end up with 0/2. So 27/2 is the result of doing this entire definite integral, or iterated integral. All right, so this is the way we're going to ultimately calculate this gadget of double integrals. And this is just an easy example to kind of show the partial integration process that we're going to do. But what are we actually calculating here? So we want to go through the setup of what are we actually doing when we look at a double integral. So let's go back. This is how we're going to actually calculate it, but let's go back and see what's actually happening. And let's go to our definition. All right, so here's the double integral. So we say the double integral of a function f over the rectangle R, and this is the notation that we're using for the double integral, is equal to, that's a mouthful there, this limit of this double Riemann sum. So let's actually go back further and unravel what this limit is actually doing. So this is how we're defining what a double integral is. And most of the time we don't calculate it like this because doing Riemann sums and then doing a limit on top of that is extraordinarily difficult. we're actually going to calculate this double integral with what we just looked at, that partial integration, the iterated integrals. But what is this definition actually doing? So let's go all the way back to the beginning. And what this definition does is it attempts to answer the volume problem. So let's suppose that we have a function, and this function is two variables. So we're going to be looking at the two variable case, and let's assume that it's non-negative. So f of xy is greater than or equal to 0, so that when we graph this function, it's above the xy plane. And not only that, we're only looking at it on a closed rectangle. So we have a rectangle where the x coordinates are between a and b, and the y coordinates are between c and d. So what we end up with is a surface that's hovering above the xy plane. So we have our surface, z equal to f of xy, and we have our rectangle R, where we have our x-axis and the y-axis. So our rectangle R is just sitting on the xy plane, and it's given by these two inequalities. And what we want to do is we want to find the volume that sits in between the surface and this rectangle. So we have all this space in between the surface and the rectangle. We want to actually calculate how much space there is. We want the volume. So that's what we're going to be after here. We want the volume of this region. So going from our rectangle up to the surface. So we have all this space here, and we want to figure out how much there actually is. So the idea is we're going to look at that rectangle first, and we're going to break that little rectangle up into a bunch of tiny little pieces, which we're going to call subrectangles. And the way we're going to do this is we're going to divide the x interval up into a whole bunch of little pieces. So this is the interval for the x coordinates. And we're going to call the width of each of these little subintervals. Well, what do these subintervals look like? We're going to index them with the letter I. So we're going to essentially, if we go back, we have our rectangle here, and here's the x direction. We're going to slice this up into a whole bunch of little pieces, all of equal width. And that's what we're doing here. So we're going to call these subintervals, we're going to index them with I, and the width of these is all going to be the same. So it's b minus a, the length of the entire interval, divided by how many there are. And then we do the same thing for our y coordinates. So we have our interval for the y coordinate, and we're going to break that interval up into a whole bunch of tiny little pieces. So again, if we go back, we have our rectangle here. Here's the y direction, and we're going to slice that up into a whole bunch of tiny little pieces. And we'll index these with j. So we're using y here. So yj minus 1 up to yj. And the interval here is the width is the length of the entire, so d minus c, divided by how many subintervals there were. And so what we're going to end up with then is a whole bunch of little rectangles, which we'll call Rij. And the area for each of these little subrectangles is going to be the width of, in the x direction, times the width in the y direction. So you want to think of these as like width. And then delta A is the area. So we're going to have all these tiny little rectangles. So let's get a picture of what this looks like. So here's our rectangle, our entire rectangle R. And what we're going to do is we're going to slice up the x direction into a bunch of tiny little pieces. We're going to slice up the interval in the y direction into a bunch of tiny little pieces. And that's going to give us a bunch of these tiny little rectangles. And the idea is we're going to look at each subrectangle and we're going to pick a sample point from each subrectangle. So, just as a little example, this rectangle here. Oof. Try that again. Yeah. Not the greatest, but this rectangle here, we're indexing the x direction with the letter I. So, and we're indexing the y direction with the letter J. So, this rectangle here, we've gone. Actually, let's pick a different one so we can actually tell. After all that, let's maybe pick the end one here. So, what do we have? Well, we've got 1, 2, 3, 4, 5, 6, 7 in the x direction, and 1, 2, 3, 4, 5, 6 in the y direction. So this would be this rectangle here, this little subrectangle. This would actually be R7, 6. And what we want to do is for each of these little subrectangles, we want to pick a sample point. So we could be systematic about this. And so we could pick, say, all midpoints. So we could do something like this. Or we could do all upper right endpoints. So we could do all the upper right corners here. So for this rectangle, I would pick that sample point. For this rectangle, I would pick the upper right corner, so that's sample point. For this one, I would pick that one again. So we could do that. And we end up with something that would look like this. So that's a perfectly oh, nope. Those aren't the upper right. So that's a perfectly reasonable way of doing it. So this is what it would look like if we're doing upper right corner. And normally you pick one and you go with it. So we do all midpoints or we do all upper right corners or things like that. Or if you wanted to, you could just do like a random pick from each rectangle. So you might do something like maybe you do something like this, and you just kind of randomly selecting a point from each subrectangle. Normally you want to be systematic, but that would be fine as well. All right. So the area for each of these little subrectangles, so each little rectangle here, all of the widths in the y direction are the same. All of the widths in the x direction are the same. So the area is going to be delta A, which is delta x times delta y. And our sample point from that rectangle Rij, we're going to call that xi star, comma yj star. So we're just calling the coordinates for that sample point, whatever we pick, xi star and yj star. So in this case, this point would be x7 star and y6 star. All right, so we've gone through, we've sliced up our rectangle into a whole bunch of little pieces. We've picked a sample point from each little rectangle. And now what we're going to do in step 3 is we're going to use that sample point to get the height of a three-dimensional box. And the way we're going to do this is the height of the box is equal to our variable, our function with that sample point plugged in. So we take our sample point that we picked in the little rectangle, we plug it into the function, and that's going to give us the height of the box for that little rectangle. So as an example, if we look at the rectangle that was in the upper, which one? This one. If we look at that subrectangle and we look at the sample point we picked, what we do is we plug the coordinates for that sample point in, and then that's going to give us how high this box is actually going to be, and then we just construct the three-dimensional box there. And so we have our rectangle R7, 6. We have our sample point here, which was X7 star, comma, X6 star, or Y6 star. And we can figure out the area for this rectangular box, or the volume rather. So the volume for this individual one, so the volume for each box is the height of the three-dimensional box times the area of the base. So the height times the area of the base. Area of the base times the height, and that gives us the volume for that. And then once we have that, the idea is we're just going to add up all of those three-dimensional rectangular boxes. And the way we do this is we can add them up in the y direction first. So we can calculate this approximation for our total volume by essentially adding up all those rectangular boxes. And what we're going to do is we're going to add up all of the, whoops, go a little bit further there. Add up all of the rectangular boxes in each column. So we would start with the I=1 column, add up the volume from each of the boxes that are sitting above each of those rectangles, and then we would go to the I=2 column and add all those up, and then we would repeat this process for I=3, I=4, 5, 6, and 7. So we're adding up the volume in each column, and then we're kind of adding then all the columns together. So this inner Riemann sum here is really, this is what's, we're adding up in each column. And then this outer one is then taking all of the columns once we've figured all those out and adding all those together. So you can kind of see how the iterated integral is going to come into play. We're going to start with the kind of the y direction, and then we're going to expand out to the x direction here. And so when we do this, the last step then is to compute the limit as both m and n go to infinity. So, and that's going to give us the exact value for the volume. And this is the definition. And so what happens as this limit for m and n going to infinity, we're going to use more and more boxes. They're going to get smaller and smaller, so they're going to better approximate the region. So this limit here means we're going to be using a whole bunch. We're going to be using many very small boxes to approximate our region. So our solid. And the idea is this limit, as we do that limit, we're going to use more and more rectangular boxes, and they're going to get much, much smaller. And we get a better approximation for what our region actually looks like. So as a little kind of picture again, go back up. This is already a pretty good approximation for what that three-dimensional solid would look like. But the idea is we're going to break these rectangles up even further. And that'll give us a finer kind of grid for what the region looks like. And so as we use more and more of these rectangles, we're going to get a better and better approximation for what the volume is. And that's precisely what our double integral is calculating. And so we'll see a little bit more behind the scenes of what this actually does, and we'll see more examples of how to actually calculate this. So we'll see you then. Bye-bye.